What we want to be able to do is to be able to better diagnose types of epilepsy on MRI scans. We want to be able to better predict how patients are going to do from epilepsy surgery and what factors will influence whether patients become seizure-free or not.
Hello, fabulous humans. Today we are talking to the marvellous Sophie Adler from UCL Great Ormond Street Hospital and Cambridge University Hospitals in the UK, who is telling us all about her Multi-centre Epilepsy Lesion Detection research project and how this enables neurologists and neurophysiologists, who do our EEGs, to more effectively identify brain lesions through machine learning. And yes, we are talking big data here, aka a lot of information. If you're already a fan of the channel, it would be brilliant if you could like this video because it makes a huge difference to us and enables more people to see credible content about epilepsy and epilepsy research. Also, do note that you can actually access more information about our guests for free via torierobinson.com. See the link below.
Thank you for having me. My name is Sophie Adler. I'm a part-time postdoctoral researcher at UCL Institute for Child Health. And I'm also a academic foundation doctor at Cambridge University Hospitals. And I co-lead the Multi-centre Epilepsy Lesion Detection, or MELD project as well.
So it's another one of those very long titles with which needs more syllables. Can you tell us about your work, please?
Of course. So the MELD project, which stands for the Multi-centre Epilepsy Lesion Detection project, is a project about trying to detect abnormalities using techniques such as artificial intelligence on MRI scans in patients with drug-resistant epilepsy.
And how does that work? I mean, so you've got your leadership role, how many people are on the team, and what's involvement like from the patient side?
So I co-lead the project with Dr. Conrad Wagstill, and we set it up probably in 2018, so a few years ago, and we have 22 hospitals worldwide that take part in the project.
Oh, great.
And initially we were working on one particular type of epilepsy, which is where a part of the brain hasn't formed correctly and causes a structural brain abnormality. And it's called a focal cortical dysplasia. And these abnormalities can be very, very challenging to see on an MRI scan. And in fact, 30 to 50% of patients their MRI scans may be initially reported as being completely normal, when actually there is this subtle abnormality somewhere. And the real challenge is finding it, because if you can find it, you can surgically operate and remove that area of the brain, and you can seizure freedom rates are around 70%. So that's really what we've been trying to do. And we have one of our studies, we had over 600 patients in it with this particular type of epilepsy, and we had radiologists from around the world from these 22 epilepsy centres would draw on the MRI scans where the abnormality was. And in some of them, they were very subtle and had been missed many times before. And then we trained artificial intelligence algorithms to try and identify those areas of the brain. And we've just released that algorithm now, and hospitals worldwide can download it and try and use it at their centres.
How exciting. You mentioned 20 odd countries. Can you tell us which countries were involved?
It's 22 surgery centres. It's not 22 countries. We have a few centres in the UK. We have a lot of centres across Europe. So Italy, Spain, Germany, and we have Finland. We have Brazil. We have America. We have China, Australia, and I'm sure I'm forgetting a few. But yeah, lots of places across the world.
Brilliant. And so to speak sort of like layman's terms, I know you said those were like focal cortical dysplasia, but can you put that into sort of like layman's terms? What does that mean for everybody? So say somebody like with temporal lobe epilepsy or, things like this. To what patients does your work apply?
Focal cortical dysplasia, this particular type of abnormality, is the most common cause of drug-resistant epilepsy in children. So it's an important cause in children. It also affects adults. It's around the third most common cause in surgical cohorts, and people who've had operations. About a third of them, the third most common cause is this type of epilepsy. It's different from, for example, hippocampal sclerosis or other types of epilepsy. So we've focused so far just on this one particular structural abnormality, which is and now we're kind of moving forward with the project, and we're starting to expand, and we're running a new study which invites patients with multiple types of drug-resistant focal epilepsies, so including things like hippocampal sclerosis.
Oh, wow. It's like your diversity in your work, which is fantastic. How will the work that you've been doing already and is upcoming, how will that benefit patients directly? I know that you said it's going to certainly remove all of the seizures statistically for 70% of patients, but how else will that positively impact the lives of these people?
So what this tool, which automatically finds these abnormalities, what we're hoping for it to do is that it will help radiologists find these abnormalities on MRI scans. So we released the tool about a month ago, and we ran a workshop to train clinicians and scientists about how to use it. And so far, we've had 6 hospitals using it as a research tool to find these abnormalities. And so the types of way we see it helping patients is that, for example, if a lot of patients with complex epilepsy will be discussed in a multidisciplinary team meeting. So that's
Yeah.
a big group meeting where you'd have the neurologists, the neurosurgeons, the radiologists, many other team members present to jointly come up with what's the best course of action or treatment plan for that patient. And how we see this potentially being used is that if a clinician is suspecting that perhaps there is this abnormality and that hasn't been seen, or they want to confirm, they think they might have seen something and they're not sure, they can run this algorithm and get a report back which will say where it's identified. And then what we're hoping is that it will either be able to help diagnose more patients, it will speed up the diagnosis, or provide confirmation for clinicians that it's the right diagnosis. So that's how we're seeing it helping patients and their families, so that hopefully more patients can be offered surgery and have the option, have those options available.
It's going to speed up effective or accurate diagnosis. Is that right? So I'm just thinking of clinicians that I've spoken to in the past. For instance, they may have seen an EEG scan, which was it was a scan from, like, say, a decade ago, and it wasn't as high quality as it may have been today. And so we may have, like, people who did not have a 100% accurate diagnosis a decade ago, but should they use your algorithm, or that their clinician use your algorithm, then they may actually get a more effective or accurate, rather, should I say, diagnosis. So, like, the diagnosis could basically change from what a person has already received in the past, correct?
Yeah, so there may be patients whose scans have been reported as being normal, and you could reanalyze them now in light of these kinds of new technologies and say, actually, was there something subtle that was missed? And I think what you're referring to is that there are different MRI scanners. So our work works using the input data that we use for our algorithm as MRI data, structural MRI data. And what a lot of hospitals have is a particular type of scanner called a 1.5T scanner. And more recently, a lot of hospitals have upgraded and now have a 3T, so a higher, a stronger MRI scanner.
One. Like the
Yeah,
latest iPhone, I guess, the best of the best that we've got so far.
exactly. And exactly like the cameras on phones have got better and better, the scan quality has got better and better. And we intentionally wanted our algorithm to be able to not just work on the latest high quality data, but to also be able to run on some of the older scans, because not every hospital has access to the latest iPhone. And so that's exactly what we've done. So our algorithm, you could run it on data from those older scanners or from the newer scanners.
That's really cool, because, like, lots of, hospitals can't afford to get a new, fancier iPhone MRI. So being able to use this system is going to prove very useful, I imagine. Now, can you tell us how, though, what your developments and your work is actually going to potentially benefit people with other neurological diseases other than epilepsy?
So this type of framework, where you analyze the MRI scans and we extract particular features from MRI scans, such as the thickness of the brain at different points, or what the intensity is on the MRI scan, or how the brain is folded, that type of analysis is very applicable to other neurological conditions. So for example, if you were analyzing patients with where there's one abnormality, or that you're looking at specific areas of the brain. So things like you could look at it in strokes, or in rare conditions in children, for example, you could look at it in a more common cause would be something like in multiple sclerosis. You could use this type of technology in MS to try and find brain abnormalities in MS. What this technology can look at is where you're expecting that there will be particular areas of the brain that might be affected and that might have an abnormality. This kind of algorithm could try and identify those areas, or using the same ideas, you could train an algorithm for your particular condition to find abnormalities. Alternatively, some of the more general things that we do, for example, like we've created an atlas of where this particular type of brain abnormality occurs in the brain. And what we found is that actually it's more common in certain areas, and there are these hotspots, and we can have this atlas, and radiologists can use it to be able to search in more detail in particular areas of the brain if they're suspecting maybe they've missed something that might be there. And so for other neurological conditions, that type of thing where you create this atlas of where it commonly occurs in large numbers of patients could be very useful. And I think that this is all really possible because of, the way we've conducted our study is an open science approach. So any hospital can take part, and we're very transparent with what analyses we're doing, and try and make any tools or code that we develop openly available that people can use it. And I think that kind of framework could be very applicable to lots of other neurological conditions where really the power is in big data. The power is in lots and lots of patients, and being able to harness information from many people.
We have lots of people who, unfortunately, for many reasons, can get a bit nervous about their data being used in along with everybody else's. Can you reassure people how their data will be protected and they will not be able to be identified as the person whose data is being used, please?
So you raise a really important point, which is about data protection and protecting patients. And so in this first study, we didn't even receive the MRI scans from patients from their hospitals. What we trained is we trained the clinicians or researchers at every hospital to be able to run some code for us, which would extract particular features from their patients' MRI scans, such as the thickness of the brain, and it would then normalize it to this template. But basically what it meant was we had no way of tracing it back to an individual patient. It was, we received basically you can imagine it like a big Excel spreadsheet, which said, at point 1 on the brain, the thickness was this, and at point 2 on the brain. So there was absolutely no way we could link back to an individual or link back to an individual's brain. We knew that a few basic information, such as the age of the patient and the sex and how long they'd had epilepsy, but we didn't know much more than that. So it was very, very heavily anonymized data. So that's one way of protecting patients and patient data and their confidentiality. In our next study, we are hoping to actually receive the MRI data, but there are different ways of protecting patients. So firstly, obviously, we don't use names or any identifiable information. So we just use a code to represent for that patient. But we can also do techniques which we can do, such as like defacing the MRI scans, so that although we can see the brain structure, we can't see the faces of patients. And that is another form of helping to anonymize patient data. So we do lots of different routes to make sure that we protect patients, and obviously also about thinking carefully about who can access the data and how it's stored safely.
Right, because people get worried that we're going to have, say, big, external corporations accessing this, and they'll use the data to more effectively target us with their marketing or something. And I know that sounds a bit out there, but these are the thoughts of people. So they need to sort of be reassured that isn't going to happen.
Definitely, I think firstly, it's important that researchers and ethics boards put in those protections to protect patients. But also, we need to talk to patients, and we need to hear what their concerns are. And so we've actually just applied for a public engagement grant to run a workshop with patients and their families for exactly that reason, to try and find out what their concerns are about data protection, what they want from this technology, and how that balance of risk, so that we can make sure our project is delivering what patients want and addresses their concerns.
I just wanted to put it out there that personally, I really don't care like how much my data is used, because I've got nothing to hide. For instance, I know there are other people out there like myself, but just for perspective, I'm not a criminal, and even if I was, I know that like my data, my health data is not gonna, to my knowledge, be used as a way to report me for crimes for which I've not yet been prosecuted and things like that. But people do get a bit paranoid about it, I think, and how potentially, for instance, again, this is going to sound random, that people's medical data could be then linked to their financial data and they could be robbed or something, which sounds to me a bit like out there, but oh gosh, our brains work in mysterious ways.
I think these concerns that everyone has are extremely valid concerns and have to be addressed, and they're important. They're big parts of our ethics applications for studies is talking about how we're going to protect data. So who will have access to it? So, for example, in our study, it's only the core research team. The data is kept on a secure academic research server, so there's no access for big companies to be able to access it. It's just our team of currently four a mixture of clinicians and computer scientists who can actually analyze the data. But there are, other people who will be able, who are collaborating with us, who will be able to help us. But it is a very protected way of handling data. And there are different approaches to how you handle data. There are also, it depends again about what patients have consented to, or whether their data is being used anonymously. So there are lots of different data protections. There are certain studies where patients have agreed for their MRI scans to be made openly available for the academic community to use, but those are different studies.
And I think another great thing about using patient data is that it's going to benefit people in the future. So it might not necessarily benefit ourselves right now, but in the future, well, without this data, we're kind of stuffed. Right? You need this data to be able to make predictions and make these calculations to benefit people of the future. And by future, it could be the people of tomorrow, like literally tomorrow, but people in 5-10 years' time.
Exactly. What we want to be able to do is to be able to better diagnose types of epilepsy on MRI scans. We want to be able to better predict how patients are going to do for epilepsy surgery and what factors will influence whether patients become seizure-free or not. And to do that, the way that has been possible is through acquiring these large data sets. So we're really grateful to all the hospitals and all the patients and everyone who's taken part in the studies, because it wouldn't be possible without them.
First of all, if we have any patients and families who would like to be involved or learn more about your work, what should they do?
You can go on our website, the MELD Project website, to hear about the work. You can follow us on Twitter, and I think Torie's going to share a link to our Twitter page about the work. And we are hopefully going to be running some public engagement workshops, and also then developing some leaflets about the about the project, which is actually the aim of the workshop, is to so that you can hear about how machine learning of MRI scans might about the research and then stuff. So yeah, that's how you can get involved.
Lovely. And what about clinicians and academics who would like to learn more? Is it the same thing? Just find you on Twitter, check out the website?
Yeah, exactly the same way, really. We are definitely recruiting hospitals to take part in our next studies. So if there are any epilepsy surgery centres who would like to take part in the MELD Focal Epilepsies project, get in contact. It's exciting to be part of it.
Oh, great. The more the merrier, I say. That'd be fantastic. Okay. Well, thank you so much for joining us today. It's been an absolute pleasure, Sophie. And and please update us in a few months' time on where you are. It's great stuff. Thank you.
Thank you very much. Absolute pleasure to be here. Thank you.